Okay, moving on. We've talked about integration as Riemann sums. Now we're going to continue talking about integration, but it's going to I'm going to lead us into connecting integration to what we've already done and why it's sort of connected. And this first part is going to be kind of confusing. You don't really need to understand really concretely everything that's happening here. But at the end, I'm going to give us the big idea that we need to take away from this. Okay, so we talked about integration by Riemann sums. Now let's consider if we have some function that is defined by an integral. And this whole premise is leading with the second fundamental theorem of calculus. This is a really profound thought about the relationship between integration and other things we've learned about. And if you're wondering, well, we haven't learned the first fundamental theorem of calculus. No, we have not learned the first fundamental theorem. That's going to go back to, going to come up later. We are going to learn it, but this second fundamental theorem gives us a relationship that I want us to have before we move on to our first fundamental theorem, which is more of applying that relationship. Okay, so when I say a function defined by an integral, what do I mean? Well, let's consider g of x equals the integral from 0 to x of 2t dt. This is an example of a function defined by an integral. G of x is defined from by the integral from 0 to x, and x is a bound of integration. That is what it means to be defined by an integral. Our x variable, our independent variable of this function, is this bound of integration right here. And then we have some function of t and taking the integral with respect to t. Okay, this part doesn't matter. This is f of t, this is dt, that'll be pretty constant. What really matters is that one of our bounds of integration, one of these numbers right here, is an x, and our function is defined by x. Okay, and now let's look at the graph of this. This is our x, and this is our f of t. And we're going to sort of do this almost like a Riemann sum, but not exactly, but still thinking of this big idea of integrals are the area under the curve. So, and I want us to find when x is 0, 1, 2, and 3. So let's just substitute in when x is 0. So when x is 0, what is the area under the curve right here? Well, this is not really any shape. That should be pretty clear that this area is actually going to be 0. When we're going from 0 to 0, this spot right here, there is no area under the curve. It's 0. And then if we go to 1, before we were using rectangles, but here we actually have a clear shape, or we could think about it as the other way we used it. This is a triangle. What's the formula for the area of a triangle? Well, that's base times height. Our base is just 1. And our height is also going to be, our height is going to be 2 divided by 2. And if you're wondering where this is coming from, this line right here is just the linear function 2t. So for every 1 we move here, we're moving 2 there. So let's, I'll go ahead and write this 4, 6. And so the area of this first triangle here is 1 times 2 divided by 2. That equals just 1. So when x is 1, g of x is also 1. I mean, I'll even do this to kind of put some separation. Okay, go ahead and pause the video now. I want you to try and find g of 2 and g of 3. It's still using the same idea. We're going to draw triangles, and we're just calculating the area of the triangle. And when we come back, I'll fill those two in, and we'll talk a little bit about it. Okay, you should have paused the video, you should have found the areas, and you'll find that the areas of this triangle, this is 2 times 4, which is 8 divided by 2. which is 4. And then this triangle, 3 times 6 is 18, divided by 2, which is just 9. So we get 0, 1, 4, 9. Okay, and we're going to come back to this in a second. But this is telling us that if we want to evaluate a function defined by an integral, we're just finding the area under the curve of that function. In this case, we use triangles, you could use squares, you could use circles, you can use whatever shape the graph ends up giving you. But okay, that's the first part there. Now the second part is actually our fundamental theorem. Our second fundamental theorem of calculus says if f is continuous on AB, which this theorem we're not going to use to really prove anything, but just so that we're consistent with how I've been referring to other theorems. If we're continuous on AB and g of x equals some function from a to the integral from a to x, so that a is just a constant up here, our a was 0, and our x was x, and then f of t, our f of t was 2t dt. So our function is the integral from a to x, where x is really the important part here. And we have some function in terms of t with taking integral with respect to t. For all x in AB, these are our hypotheses. Then our conclusion is that if we take the derivative of g of x, that's just going to give us f of x. And this is really our important thought here. This tells us about the relationship between integration and differentiation. So if I were to go over to my, back to my sort of example up here, g of x equals the integral from 0 to x of 2t dt. And I want to differentiate this function, so I say d over dx of this function, gx equals 0 to x 2t dt. If I want to find the derivative, well, the derivative of g to the x is just g prime of x. And my second fundamental theorem of calculus lets me say that, well, I can just take this x and substitute it in for t, so I get 2x. And before I say our final takeaway here, g prime of x equals 2x, I want us to go back up to our table, and I want us to make an observation about this. If you were to see a table that looks like this, what would you say this function is? What does this function look like? Well, we're going +1, we're going +3, +5. And I don't know if you, sorry, I don't know if you've ever learned this sort of trick before, but if you look at, we can tell that this function is not linear because it's going +1, +3, +5. It's not a constant rate of change. But if I look at the rate of change of the rate of change, it's going +2, +2. Well, that tells me that the rate of change of the rate of change is constant. And that actually is part of our definition of a quadratic function. And if you think about it, well, I don't have to say that part yet. But this is a quadratic function. And it goes 0, 1, 4, 9. Well, this is just x squared. G of x is just x squared. And well, if we take a look, g of x is x squared, and we said down here, by our second fundamental theorem, g prime of x equals 2x, well, what is the derivative of x squared? The derivative of x squared is 2x. And that is really where I want to get to our big idea, this idea of the relationship between differentiation and integration. And it turns out that these two operations, let me choose, I need a super good color for this. Let's do this pink reddish color. Differentiation and integration are, drumroll please, differentiation and integration are inverse operations. Boom. Actually, I don't want to say operations because I'm not sure if that's formally correct. They're inverses. Differentiation and integration undo each other. So if we take the derivative of a function that's being integrated, we get rid of the integral, effectively. And if we integrate something that's being differentiated, then the differentiation goes away. And I'll talk more about that later. But this is our big second fundamental theorem of calculus. And this is the big idea I want you to take away, that these two things are inverses. If I take the derivative of an integral, the integral goes away. If I take the integral of a derivative, the derivative goes away. Which I'll sort of show example. That'll come up later, but if we look here, we can clearly see that I took the derivative of an integral and the integral went away. We were left with 2x. And the other way I'll show shortly after. And that's all I have to say for the second fundamental theorem. I'm going to do another video that's going over some example problems because applying this theorem is a little bit harder. The problems they're going to ask are going to be tricky, but our big idea, these are inverses. Boom.